right, so back at vectors here. At this point, what we have done already is found a unit vector in the direction of a particular vector that was given. And we did that, actually, we did that for component form, and then we also did it for linear combination form, meaning with the I and the J. Okay, so now we're going to look at finding a vector with a specific magnitude in the same direction of another vector. So this kind of starts out sounding a little bit like what we did with the unit vectors. It says in the same direction as this vector. So we found a unit vector in the same direction as that vector. We know how to do that. So here's all that we have to do for this type of problem. We do the unit vector that's in this direction, and then we multiply it times the magnitude. I find my unit vector for this, multiply times 5. I'll be done. Okay, so let's go ahead and do that. To find the unit vector for u, I take u and divide it by the magnitude of u. Well, the magnitude of u is square root of -3 squared plus -2 squared, which is 9 plus 4, which is 13. We keep bumping into this particular value. All right, so if I'm going to do the unit vector in the direction of this, there's the magnitude, and all I do is I divide these by that magnitude. So I get -3 over root 13 and -2 over root 13. But we're not allowed to leave it like that because we have radicals in our denominator, so we can't do that. So we're going to have to rationalize those denominators. So I multiply on top and on bottom by square root of 13, and I get this and this. Now, this is a unit vector in the direction of u. I want a vector in the direction of u that's not a unit vector because I don't want magnitude of 1, I want a magnitude of 5. So basically I'm just going to multiply that times 5. So 5 times all of this, which gives me -15 root 13 over 13 and -10 root 13 over 13. If I found the magnitude of this, I would get 5. How do you find the magnitude of it? This squared plus this squared, square root of the whole thing. That would give me 5. You're welcome to check it. Okay, let's look at another one. This time, same exact thing, but instead of being written in component form, this is written as a combination of I and j. So let's go ahead and think of that in component form, and then it becomes the same thing. This is my component form. So the magnitude of it is the square root of 2 squared plus 3 squared, and I have got to stop picking the same values. I'm not really sure why I am. 4 plus 9 is 13. So now I'm going to take 2, put it over square root of 13, 3, put it over square root of 13, and this is a unit vector in the direction of the vector 2i plus 3j. Now I need to rationalize the denominator, so I get this. This is a unit vector in the direction of 2i plus 3j. However, it's a unit vector. Unit vector means magnitude 1. I want magnitude 6, so I just multiply this by 6. And that gives me 12 root 13 over 13 and 18 root 13 over 13. And this is my answer. Okay, let's look at another one. This time it is in the form of being a sum of those two, the horizontal unit vector and the vertical unit vector, I and j, but I don't have a j. So this is the same as just -4, 0. That's what this is the same as. Now -4, 0 says my vector goes 4 to the left, 1, 2, 3, 4, and 0 up and down. Okay, so if I want a vector that goes in the direction of this and has a magnitude of 5, I already know what the unit vector would be in this direction. It would be -1, 0. In order to go straight to the left, not up or down at all, and be a unit vector, then that means you have to go left 1. So this is that vector. This is the unit vector that goes in the direction of this vector. If I want a magnitude of 5 instead of a magnitude of 1, then this is what I have. And that's how you do those. All right, let's move on. Okay, the initial and terminal point of a vector are given. So this is another type of problem. Write the vector as a linear combination of the standard unit vectors I and j. This is even a little simpler than what we just did. Okay, the initial point, terminal point. So if the initial point is at, and I'm just going to sketch a graph, -1, 4. Sketching the graph just helps me have some perspective to make sure I'm kind of thinking of it in the right way. Terminal point is 3, -6, so it's way down here. So it goes from here to here. So it goes down and to the right. Okay, so that means to the right would be a positive x, down would be a negative y. Another way of thinking about this is your x is your horizontal component comes first, so it's positive for I. It's going to have a positive number in front of I and a negative number in front of j. But let's go ahead and figure out what our displacement is here, or what our horizontal displacement is and what our vertical displacement is. Okay? That's basically just drawing the right triangle. From -1 to +3, I have a horizontal change of 4. From +4 to -6, the vertical change is 10. So in component form, this would be +4, -10, because I'm going to the right and down. If I write it with the I and j, all that changes is I just say that's 4 times I minus 10 times j. And if you wanted to work it out, you could. Like I showed you earlier, this means 4 times 1, 0, minus 10 times 0, 1. This would be 4, 0, minus 0, 10. And that would be 4, -10. But this is the answer. This is just checking it. Okay, that's pretty straightforward. Let's do another one, another type of problem. Find the magnitude and direction of vector j. This one we need to do a little bit of thinking about first. Okay, this is this whole, what on earth is that? Well, ideally, in your textbook, you would have done the trig unit before you got to this. We haven't, though. The order in which we do this is different. But the good news is this is not going to be that hard, especially because the values that we're looking at, if you really wanted to check those out, they're sort of special right triangles. But we don't even need to go that far, honestly. Okay, this says 4 times cosine 60 of I plus sine 60 of j. Let's look at a unit triangle or unit vector. Random unit vector. Okay, let's say I have, let's not be so random after all. Let's go ahead and talk about 60. 60 degrees, unit vector. Unit vector means its magnitude is what? 1. Okay. So let's say I wanted to find this distance right here, this horizontal distance. Okay, I'm going to go ahead and call it A. And let's say I wanted to find this vertical distance, B. Because remember, that's what goes in front of I and J, is the horizontal distance and the vertical distance. Horizontal component goes in front of I, vertical component goes in front of J. Well, I can use right triangle trig, good old standard right triangle trig, to figure out my A and my J. Excuse me, my A and my B. So let's go with A first. You can't do them both at the same time. So let's go with A first. A is adjacent to the 60-degree angle. The only other side we can work with, because it's the only other side we have, is the 1, which is the hypotenuse. So we're working with the adjacent and the hypotenuse. What's adjacent over hypotenuse? Well, it's cosine. So cosine of 60 equals adjacent over hypotenuse. Well, what's anything over 1? It's just that. In other words, this is just cosine of 60 equals A. So this value is just cosine of 60. So for this triangle, my x value, my horizontal component, is just cosine of 60. Guess what's going to happen when we do the other one? You probably already know. Opposite from 60, this is the opposite side. This is the hypotenuse. Opposite and hypotenuse is sine. So sine of 60 equals opposite, which is b, over hypotenuse, which is 1. B over 1 is just b. So the sine of 60 is just b. So again, my vertical component here is just the sine of my angle. Well, that's kind of how it's going to keep working. Your horizontal component is the cosine of your angle, and the vertical component is the sine of your angle. So this is the horizontal component. This is the vertical component. So the direction of this particular vector is 60 degrees. Okay, because a vector that has a horizontal component of cosine 60 and a vertical component of sine 60 is 60 degrees from 0. Remember, the right hand side, or the positive x-axis, is your 0. So this direction is 60. So direction is 60. Well, if we look at this, we had a unit vector here. So this is a unit vector. Unit vector means magnitude of 1. But do you remember what we did on the last set of problems? If we wanted the magnitude to be bigger than 1, we just multiplied by a number. So this has a magnitude of 4. Okay, let's look at another one. Couple of ways we could look at this one. We could put it in component form and find it that way, because this is pretty close to component form already. Or we could, let's see what happens if we factor out that 4. And this is negative 1i plus 1j. Or in component form, that would be just negative 1, 1. Well, the direction, negative 1, 1, if you go negative 1 and up 1, we're going just as far to the left as we are going up. This is a nice little square. Mine doesn't really look square, but it is. So this is right in between this axis up here, the positive y-axis, and the negative x-axis over here. It's exactly in between, because you're going over 1, up 1. Kind of like if I were graphing a line and I was going over 1, up 1, left 1, up 1, that would be a line with a slope of negative 1 straight through the origin in a perfect diagonal, meaning what is this angle on either side of here? Well, if it's right in the middle and this whole thing is 90 degrees, this is 45, or you could say this is 45, which means the direction from 0 over here is 90 plus 45, which is what? 135. So that's my direction. My direction is 135. What's the magnitude? Well, that's part of why I factored this out. Because remember, when we had a 4 out here, that was going to give us the magnitude. The only problem with that here is that this is not a unit vector. Okay? Negative 1i plus 1j is not a unit vector. Because if we do 1 by 1, 1 squared plus 1 squared gives us square root of 2. Okay? So I'm going to do that. Find the magnitude of this vector. It's square root of 2. 1 squared plus 1 squared is going to be square root of 2. By the way, that goes with the fact that 45, 45, 90 triangles, you take the leg and you multiply by square root of 2 to get the hypotenuse. Same thing. So 4 times this, which just gives me 4 root 2. So these are my answers, 135 degrees and 4 root 2. All right. It might have been easier on that one to just go ahead and change it to this and then do it that way. Okay? You get the same thing. You put that in the Pythagorean theorem. You get 16 plus 16, which is 32. Square root of 32 is 4 root 2. Okay? Last one. This one we can't really kind of figure out like we did the whole 45-degree angle thing. This one we actually have to use our tangent to figure it out. So 4i minus 7j, you're going 4 to the right minus 7, it means down 7. There's my picture. This is my angle. So inverse tan of 7 over 4 is going to give me this angle, and I don't have a calculator handy, so let me see if I can grab one. I get 60.25, 60.26 really. So this angle is 60.26. Now if this were physics, we could say 60.26 degrees south of east, or let me subtract from 90. Which I could do in my head, but instead I'm using this, aren't I? Kind of didn't think about just doing it. Or really we'd probably say 29.74 degrees east of south. Excuse me. Yeah, that's right. East of south. I'm not used to thinking of it that way. All right, but we don't do it that way. We start at 0 and go around. When you go around like that, you'll notice that the only part that's not all the way around the triangle, in other words, this is the only part that's keeping us from completing our circle, is the 60.26. So 360 minus this portion will tell me how many degrees I've been around. So 360 minus 60.26 is 300 minus 0.26, which is 299.74 degrees. Okay, now in terms of magnitude, I'm just doing my Pythagorean theorem with 4 and 7. So I've got 4 squared plus 7 squared, and then I'm taking the square root of 65, and that cannot be simplified. So I would just leave it like that. Here is my magnitude, here is my direction.